And welcome everyone. Thanks for joining us as we introduce the 3D REDI to you today. Just to start with, I'd like to give a bit of an introduction to TRICEP, which is the facility and the team that developed 3D REDI, and just explain the capabilities and expertise that's available within that entity. Let me first of all say that TRICEP arose from a very important partnership between an entity that's headquartered here at the University of Wollongong, that's involved in very fundamental research, blue sky discovery research, and also the ANFF materials node, which is involved in facilitating the translation of research into real world applications. So the Fundamental Center of Excellence that's headquartered here at Wollongong is ACES, the ARC Centre of Excellence for Electromaterial Science. It's a national centre of excellence with nodes in each of those Australian universities and international nodes at each of our partner universities mentioned there. The core role of ACES is the design and discovery of new electromaterials, and to couple those with other advances in materials, as well as advances in fabrication, to create devices and structures that have real application in energy and also in health. So we're positioned to take the most fundamental discoveries of a new material and very rapidly translate that into devices and structures to get the benefit out of those new materials. And what's facilitated us in being able to do that is we're also the headquarters for the ANFF materials node. And in the ANFF materials node, we have scalable materials processing capabilities. So a material discovered 1 week, we can look at the scale up of the chemistries for that material and deliver scaled up capabilities rapidly. We have customized fabrication hardware, which enables us to create prototypes and structures and devices that integrate those scaled up materials, and also a suite of innovative characterization tools, which enables us to not only characterize the individual materials that might go into those structures, but to characterize the performance of the devices that are created from those innovative fabrication tools. So TRICEP established a couple of years ago now with the support of the University of Wollongong and also the ANFF materials node and ACES, and with some support also from MTP Connect, was set up to take fundamental discoveries and particularly in this area of health, work with our clinical network to see how we could use 3D bioprinting to realize scalable commercial opportunities. And we've been looking at doing that now over the last 2 years. We have a demonstrated capacity to identify and formulate new bioinks and take that right through to delivery to our collaborators and customers, and also to identify and develop customized bioprinters depending on the clinical solution that is required for a particular challenge. In terms of the bioinks, we've developed quite an extensive inventory of bioinks, all of them based on naturally occurring components. Many of those now sourced in Australia, and that's been a bit of a change from when we first started TRICEP. We've really grown our Australian source base for these naturally occurring materials that we use in the bioink formulations, and the others are sourced through important collaborations with other partners overseas. And as it says down the bottom, it's not just about identifying the source here at TRICEP, it's about scaling the synthesis, developing the appropriate packaging, sterilization and transportation means for those inks to get them to our customers in the same form as they leave the TRICEP facility. And those bioinks, of course, have been developed and customized for a whole range of clinical applications in mind, whether that be for neural cells, muscle cells, stem cells, or other types of cells, depending on the application at hand. And those applications are driven very much by our clinical network. Clinical collaborators established around Australia and indeed around the world at the moment that work with us on cartilage regeneration, Peter Chung and Claudia DeBella, and in areas of 3D printed ears with Dr. Pale Mukherjee here in Sydney, with Dr. Toby Coates in islet cell transplantation, and Dr. Jared Sutton in 3D corneal repair and eventually bioengineered corneal regeneration or replacements. So there's many others on this screen, but I just highlight those. They're ones that are really developing down the translational pathway for us at the moment. And each of those has required the development of a customized delivery system. The 3D ALIC for the printed ears, the iFix pen for Jared Sutton for printing directly into the eye, the Excel to BioPen for cartilage regeneration, and the 3D PICT that you see here for printing structures containing islet cells for transplantation into patients to treat diabetes. Many of these projects have been ongoing for a number of years, and so we've learned a lot in the design and development of 3D bioprinters from our customized printer program. And we've used that knowledge in order to deliver, as you're going to see, the 3D REDI. So it's based on a lot of input from collaborators all around the world, from our clinical collaborators, from the scientific, engineering and clinical team that we have on hand through ACES and the ANFF materials node. And of course, many of our collaborators also based overseas. At the moment, we have versions of the 3D REDI with our partners at Asan Medical in Korea, with the Rizzoli Institute in Italy, and Yokohama National University in Japan, and a number of collaborators around the country here in Australia. And we'd like to thank those collaborators for taking on those early versions of REDI that's helped us to get to the version that we're at today. And those others on the screen are pending deliveries to our collaborators of this current version of 3D REDI. So the establishment of TRICEP with the support of ACES, the ANFF materials node, and the University of Wollongong, we've already demonstrated the ability to deliver customized bioinks in a usable form to collaborators and customers around the country. We've already demonstrated the ability to prototype customized bioprinters for a range of clinical applications. But today really is a first. It's a first for TRICEP because today we're going to introduce a printer which is readily available. It's a more generic printer, which is based on those years of knowledge and expertise coming together. A generic printer that's put together to facilitate research and research training using 3D bioprinting, a very robust platform, a robust and versatile platform. So it's great for us. We're excited today. We're excited because we're bringing to you 3D REDI, and it's not just a product, it's not just a printer. It's a collection of knowledge and ideas that's really been collected over a number of years. So it's great to see it all come to fruition, and we're proud of it. And I'm certainly proud of what the TRICEP team has been able to pull together on this.
So just to give you everyone an overview of the 3D REDI and the capabilities and how we've come together with it. So the system is a very small form factor system and allows you to easily deploy it within a laboratory environment, a training environment, or indeed into a biosafety cabinet. And the system is operated directly from a laptop PC and is self-contained. So there's no longer the need for pneumatic compressors or any other ancillaries. So this system is set up around a geared stepper motor mechanism, allowing us to have full control over two materials as they're being extruded simultaneously. The system is quite robust, with linear guides ensuring that there's no variation in the plungers as they're being extruded. Initially, the system is set up around the 3cc syringe carrier, a normal volume of material to allow you to refine your printing parameters as well as produce initial test prints. In case where there's a limitation or the resource is limited, you may be able to reduce this down to 1 cc syringes. The system is built around temperature management systems to allow us to maintain the materials between 10 and 40 degrees, ideal for allowing us to modify the viscosity or to maintain cells at temperature. We've incorporated a variable intensity UV or blue light LED into this system, allowing us to have full control over the cross-linking density of materials that have been deposited. And this is quite different to other systems available on the market, where we can then incorporate functional grading within the structure based on the cross-linking density. And of course, it all combines with the TRICEP coaxial tip, which allows us to have a very small dead volume of material, minimizing that down into small 200 or 300 microliters of material, which we can then retain and allow us to extrude materials coaxially in a core and shell configuration. The substrate holder is quite refined, allowing us to be very flexible in retaining either glass substrates or indeed any size of Petri dish that may be required. The system has been designed specifically with research and education in mind. And in terms of education, we've built 9 hours of tutorial packages around this system that allows you to develop the skill sets that are essential in starting out in the biofabrication space. Obviously, we have to supply a starter kit with this system. This allows you to get up and running along with our tutorial packages, which I'll mention later, shortly. And as a key component of this starter pack is the materials that have been supplied by TRICEP. So our Gelma-based material and our photo initiator. Those are supplied to allow you to perform the tutorial packages, and then all the ancillary components, including multiples of our coaxial tips, any of the custom tools that are required to operate the system, and guidelines on all those. Software is another key focus of this system. As technologists, we want to be able to access as much functionality as possible. But I must stress here that we've set it up so there's 2 different grades of software. The software grades are for the novice and for the more experienced user. And as you go through the novice course, you'll then have full access to all capabilities. Software obviously allows us to define what configuration the printer is in. So the system has been built up around a modular framework that allows us to then, in the future, add additional componentry, which includes microvalve droppers and additional components. We obviously have manual positioning of the system, which Cameron is going to demonstrate for us shortly. We have a macro function to allow you to predefine any of the prints that you want to produce and allow you to repeat those prints very easily and quickly. We have incorporated a gradient structure function that allows us to have control over the ratio of the materials as they're being extruded, allowing you to develop functionally graded structures. And then again, we can incorporate additional user profiles. So you can have multiple users using the platform and operate under their own profiles. The practicals are a key component of this system, allowing us to first of all set up the printer, introduce the students and researchers to bioprinting and its applications through assembling the printer itself and running through manual calibration and optimization of the adaptable software. In the second practical, students are then able to run with a single material. In this case, Lutrol is a demonstration material, allowing to vary the parameters and determine what effect that's had on the print properties, as well as optimize those properties to get target print quality, and understanding how those parameters are affecting the system as it operates. In the third practical, the students are introduced to the coaxial extrusion nozzle and using Gelma, or the TRICEP supplied Gelma, to vary the cross-linking density of the material and characterize how that affects the modulus of the printed structures. As Gordon's mentioned, we also have these systems already distributed around some of our collaborator research networks. You can see just a representation of that there. Systems are being delivered in the very near future. And now what we're going to do is pass over to Cameron, who's based in TRICEP, and is going to run us through a 3D ready demonstration.
So welcome to the live demonstration component of our REDI launch. I'll just do a brief talk through of some of the additional software features, and then I'll jump right into a demonstration print highlighting all of our key capabilities. So as Steve already highlighted, there's area in the software for setting what configuration of components you have on the machine, as well as all the expected manual controls you'd see on any sort of printer. What I've done over here is I've taken our lattice creators and our spiral G-code generators and such, and I've chopped and changed them into a custom macro. And this is something that any user will be able to do to incorporate complex features into single print processes. So cutting over to the close-up view of the printer now, I'll hit run macro and we'll see the print begin. This first section is a functionally graded two-line scaffold, which shows it going from completely shell material to completely core material and back again. The structure of our coaxial nozzle, which camera am I on? That one. is shown here with our red material representing the shell and the blue material representing the core, with the capability to fully or partially encapsulate the core material during printing. Once this line finishes, it'll move to a two-layer scaffold, one of the more common structures printed during research of tissues and cell printing. This lattice will also be a coaxially printed lattice with the core fully encapsulated. You'll notice that at the beginning of this scaffold, it can jump straight into the fiber that it is extruding. This comes from a level of tuning for the materials for the print process, with appropriate extrude and retracts to prevent oozing. Now, with our lattice creator, the number of pores and the size of the pores, the amount of flow rate, all are easily customizable to mix and match these structures to whatever your application requires. Next up will be a spiral print. The spiral prints are used to make discs of non-porous hydrogels with a material encapsulation in the center as well. This has the capability to be run as multiple co-printed spirals, several layer spirals, even a dome spiral. And this spiral functionality is a demonstration of our ability to adapt and customize our software for user requirements. This was a feature request from a user. After this spiral finishes, it'll demonstrate the photo cross-linking process with our onboard 4 or 5 nanometer LED. At the beginning there, it did show a ramp up of the power from 0 to 100. I made it a bit too fast to show it was there. And that is the capability of the 3D REDI. I'll hand back over to Stephen Gordon.
I'm just going to kick off. I see there's a couple coming in, but just with Steve and Cameron. Well, this has been set up as a research and training tool, but it's also a platform, as you've probably heard alluded to, that can be modified for particular research projects. And one project that has already been critical to developments in, and that is our islet cell transplantation project, where we need to print multiple types of cells and multiple materials. And that's required the addition of an extra head to the 3D REDI, but maybe Steve could just comment on how easy it is to build on this platform going forward for particular research applications.
Yeah, well, Sam is looking there at the close-up view, and on the close-up view, you can see how we can easily modify the substrate holder, and that's the first port of call. So we can modify what we're retaining on the substrate. Cam is very nicely demonstrating that for us. That can be interchanged. If we've got a specific substrate that we want to print onto, we can modify that to suit. In terms of the printer itself, it's demonstrated today with a coaxial print head. We are able to run it in a single material mode, and in the future, we'll also have a mixing head mode that will allow us to blend two materials together. In terms of adapting it and allowing additional functionality, it's provided with the two base extruders, but it also has the capability to include microvalve droppers, spray heads, a range of other components that are easily incorporable.
I think that answers our first question about the coaxial head. I mean, basically the head can be modified, obviously to go as a uniaxial, or we can add other additional features to it. So there's a lot of flexibility in the print head for Marcia there. For Jigu, excited to see the launch of 3D Ready. Oh, just congratulations, and to see the improvement as we go from version to version. I think each time we get the 3D Ready out into another laboratory, we do see suggestions come back, and that's great as a research and development team for us to get that feedback and see what other challenges we need to embark on. And then there's G also has mentioned what's the resolution of the Ready and whether the platform has temperature control.
So that then resolution is 25 microns X and Y, and then slightly significantly higher resolution in the Z axis. In terms of temperature control, there will be an add-on feature to allow temperature control on the base. So again, temperature range of 10 to 40 degrees.
And then in China, so we're going to have a number of Redis available, and obviously looking at particularly getting those out to our collaborators in the first quarter of next year. So yeah, we should talk about that. Does it have a piezo head for cell printing?
Not at present. We don't have a piezo head, but there is a microvalve dropping head that can be incorporated in one of the BioWings.
Oh yeah, sorry. So maybe some idea of the types of BioWinks that we're looking at the moment. But one of the most popular is around the Gelma base. Also, alginate, of course, has been a basic component of BioWinks for a long period of time. Nanocellulose is another very common material that we're developing as a major component of BioWinks. Chitosan as well is a component of a number of BioWinks. And there's carboxymethylcellulose as well. And there's some more specialist ones, which are materials quite unique to TRICEP and its partners. One of those is Ulvan, which is sort of the equivalent of alginate, but from a green seaweed, and has much higher bioactivity than alginate. And that's a BioInk that we're working with our partners to launch on the scene in next year. So that'll be an exciting development on the BioInk front, which of course could be used with the 3D Ready going forward.
And then Marzi has asked about the pressure system. Yeah, it's mechanical extrusion, so there's no pneumatic system. It's a forced volumetric control system based on a stepper motor.
And I think Jirai is asking about collagen. Yes, we do quite a bit of work on printing collagen, Jirai, particularly for our IFIX system and our corneal bioengineering system that we're working on with Professor Sutton. Of course, the sources of collagen are also very important, and that's actually quite a challenging one. All of the others I mentioned before, we have good, reliable, inexpensive sources of quality materials. When you get into collagen, there are some real challenges in that sourcing and quality and reliability and cost for those base materials. That in itself is a project that we're running within TRICEP and with our collaborators and within ACES as well, is all about comparing and identifying the sources of collagen. And we're very keen to pursue the identification of appropriate marine sources of collagen. That's something that's high on our agenda at the moment.
So uniform flow of ink is ensured because it's a mechanical positive displacement system. So as the lead screw is rotated, you've got a constant force, very similar to a syringe pump mechanism.
Yeah, so in terms of procurement, we'll have all of those details rolling out in the first part of next year on the TRICEP website. We're gearing up to produce a number. We have a number available already, but most of those are earmarked for collaborators at the moment. So we're interested. If anyone on the screen, and there has been a couple of mentions, of course, if you want to contact us and say that you would be interested in acquiring one of the 3D Redis, then we'll get you on our list, and we'll keep in constant communication as our fabrication manufacturing line gears up in the first part of next year.
Ozzy has also asked about the pressure range. It's not a pneumatic pressure, so it's a mechanical force. So the extrusion force is in the range of consistently 40 newtons. That'll change based on the extrusion nozzle that you're using, as well as the syringe diameter. So you tune those two, and either you tune your syringe and your extrusion nozzle to be within the max force range.
Yeah, and I'll just ask Cameron a question. I think we talked about the tutorials. Cameron, you've worked with a number of students in developing the tutorials and then testing them out. Can you give people an idea of the length of time it really takes to become proficient with the use of the tutorials and taking on the printer operation individually, without supervision?
Yeah, so I've had a few students run through the practicals independently, with me just providing the required materials. And it's been about 5 hours. One student was able to get through it all and was very confident in using the system independently. And so in less than a day, you can have users up and running on their own.
Great. And so people could basically do the 3 tutorial sessions in one day?
If they were astute and done the pre-reading, then yes.
Yeah. Okay, good. About delivery into India, we actually have on our books at the moment, we will be delivering a 3D Ready into India is our plan in January next year. And the first one will be to AMTZ in Vizag in India. But of course, we know we are talking to many collaborators in India that would like to have access to a robust system like this. So yeah, please just keep in touch with us around that. Yeah, I think the function of the UV in the chamber, I assume you're talking about a biosafety cabinet there. I don't think you'd replace that by anything that the 3D Ready can do. You would still need to have all the capabilities and functions that a normal BSC normally delivers. What we've done is built the Ready to a size that it's can be accommodated in just about any standard BSC. So we're not aiming to replace any of the normal functions of the BSC. Okay, if there's no other questions, I'm going to thank you again. And we got another one. Okay, thank you, Turai, for that. Let's keep in touch. So I was just going to say, yeah, please do keep in touch with us. If you've got any other questions, just email Steve or Cameron or myself, and we'll get back to you with answers. As I said at the start, we're incredibly excited about this coming to fruition of the 3D Ready. It's taken a long time and pulled together a lot of knowledge and expertise over a number of years. And so we're keen to share it with as many people as possible. And it'd be good to work with you even in what remains of this year to make sure that we can get the pipeline ready to get the 3D Ready delivered as we charge into an exciting 2021. And thank you all. And I'll thank Steve, and I'll thank Cameron, and I'll thank Sam, the man behind the camera. And we're going to sign out from beautiful Wollongong and wish you well wherever you are. And we'll keep in touch with you all. See ya. Bye-bye.
Thank you, guys.